Okay. Okay, so now I'm recording. So, okay, so I was saying if P is a topological operad, chains over R applied to P is an operad in chain complexes of R modules. And similarly, the homology of P with coefficients in R is an operad in graded R modules. And the reason for this is that both these functors, singular chains and homology, are what's called lax monoidal functor. So lax monoidal functor will imply sort of by abstract diagram chasing, this will imply that when you apply it to a topological operad, what you get is an operad in the target category, either chain complexes or graded R modules. Okay. And now we can make a definition. I'm going to say that a topological operad is formal over a ring R if there exists a zigzag of quasi-isomorphisms of DG operads connecting singular chains on P with coefficients in R to homology on P with coefficients in R, where I view this object as a DG operad with trivial differential. So any graded R module, I can view it as a chain complex with trivial differential, and similarly, an operad in graded R module I can view as a DG operad with trivial differential. So this is a definition of being formal for an operad, and this looks a bit different from the very first theorem I stated. Because in the very first theorem I stated, I was a bit more specific. I was saying that you could find a zigzag of length 2 connecting chains on the little disks operad to homology. But in fact, this is something you can do in general. So you can prove that there exists, sorry, I forgot the word model category. So there exists a model category of DG operads in which all objects are fibrant. And well, if you don't know what a model category, that's fine. That's not something I'm going to use very much in this talk. But one consequence of this construction is that this definition over here is equivalent to this definition where I require my zigzag to be of length 2 like this. So topological operad is formal if there exists a zigzag of quasi-isomorphism of DG operads with only one term in the middle, which is quasi-isomorphic to both chains and homology. So what I'm saying is, whatever, whichever zigzag you find connecting chains and homology, if all the maps are quasi-isomorphisms of DG operads, you can always reduce it to a zigzag of this form. Okay. So that's a definition. That's what a formal operad is. And now, using this definition, I can rephrase Kontsevich-Tamarkin theorem as saying that the little 2-disk operad is formal over Q. So let me recall what the little 2-disk operad is first. So it's a topological operad which is given in arity n. I consider the space of what I denote framed embeddings from a disjoint union of n copies of the disks to the disk D. So D is the unit 2-disk. And by framed embeddings, I mean the space of embeddings whose restriction to each disk is a composite of a dilation and a translation. So my disks are not allowed to rotate. They're just allowed to translate and shrink. And up to what you see from this definition is that up to homotopy, the scaling factor, it lives in a contractible space. So up to homotopy, all that matters to distinguish a point in the space of embeddings is where the center of each disk goes. So in fact, this space is homotopy equivalent to a space of configurations of n points in the disk. And this is also homotopy equivalent to a space of n points in the plane. But the operad structure is given by composing embeddings. Okay, so now I can state again the theorem of formality, and now we're supposed to understand all the terms in that theorem. So I'm claiming that there exists a zigzag of quasi-isomorphisms that connects the singular chains of the little 2-disk operad with coefficients in Q to the homology of the little 2-disk operad with coefficients in Q. And well, before telling you a little bit about how one can prove the theorem, let me tell you one very important consequence of the theorem. And this is what's called the Kontsevich formality theorem. So it states the following: if you take an associative algebra A over a field of characteristics 0, you can form the Hochschild cohomology of A. And actually, it's a result of Gersten-Haber that this collection of vector spaces. So this is a graded vector space, but in fact, this graded vector space admits the structure of a Gersten-Haber algebra. So an algebra over this operad here. And on the other hand, you can also form the Hochschild cochain complex. So this is a cochain complex whose cohomology is this. And it turns out that this cochain complex admits the structure of an algebra over the singular chains of the little 2-disk operad. And well, this is a statement that's called the Deline's conjecture. And it's no longer a conjecture, but there are several names attached to it. So there's been several proofs in the literature. So usually people just call it the Deline's conjecture, even though it's not a conjecture anymore. And maybe some names I can mention. So I can mention are Tomarkin and Seguin. I'm sure I'm going to forget some. There is also a more general proof by Justin Thomas. Well, Kontsevich gave a sketch of a proof. There is also a proof by Jacob Lurie. So there are several proofs of this result in various levels of generality. But what you, what we see from this is that, well, using this zigzag of quasi-isomorphism, we can in fact view both of these objects as algebra over the same operad. So this one is an algebra over Gerst. So since we have this map, it's also an algebra over this middle term here. And this one is algebra over chains of D2. So using this map, we can view it as an algebra over the middle term here. And this middle terms, it turns out, we can choose it to be an operad. Well, there is an explicit model called Gerst infinity. So in fact, we can view both of these objects as algebra over the operad Gerst infinity. And here's a theorem called Kontsevich formality. If A is the algebra of smooth functions on a differentiable manifold M, then the Hochschild cochains over A is quasi-isomorphic to the Hochschild cohomology of A as Gerst infinity algebras. So of course, if I remove this word, over a field, any chain complex or cochain complex is quasi-isomorphic to its cohomology. So this is not much of a theorem. But what's hard about the theorem is that you can pick this quasi-isomorphism to be compatible with this algebraic structure that you have on both sides. And it turns out the right-hand side you can compute. There is a theorem of Hochschild, Constant, Rosenberg that tells you that the right-hand side is what's called the algebra of Pauli vector fields. So you take you take the tangent bundle of M, you take the exterior algebra and the tangent bundle of M, and then you take global section to this. So that's what, conservative formality gives you a computation of this object so it tells you that this object is quasi-isomorphic to this object. And what is the motivation behind this theorem? Well, it turns out that this operad Gerst infinity, it contains a suboperad and a operad called L infinity. So in fact, these two objects are quasi-isomorphic as L infinity algebras. And this is very important because this L infinity algebra is what controls deformations of the algebra of smooth functions on M. So more precisely, well, you have you can classify deformations of the algebra of smooth functions on M as you can put them in one-to-one correspondence with equivalence classes of Moore-Cartan's element in this L infinity algebra. And similarly, so according to his quasi-isomorphism, deformations of A are going to be controlled by this much simpler L infinity algebra, and that's how Kontsevich proves that for Poisson manifolds there is essentially a unique deformation of the algebra of smooth functions. Which, because the Poisson structure is exactly going to correspond to a Moore-Cartan element in this L infinity algebra. So yeah, so the motivation was coming from physics. The idea is your algebra of smooth functions is a physical system. Well, sorry, the manifold is a physical system, and then if you want to quantize your physical, like your manifold is a classical physical system, and then if you want to quantize it, you would like to find a deformation of your algebra of smooth functions, which is not necessarily commutative. And this is what this L infinity algebra classifies. So anyway, this is not something I want to tell more about, but this is this gives you one motivation for why this theorem is important. I mean, you don't even know how to formulate this theorem if you don't have access to this theorem. Okay, so now, well, let me tell you how one can prove a theorem like this. And I'm actually going to start by considering a simpler situation, namely the situation of proving formality of a commutative differential graded algebra. So here's a theorem due to Sullivan. If I have a simply connected finite type commutative differential graded algebra over K, a field of characteristics 0, and if I have alpha an element of infinite order in the units of K, I assume that I can find an endomorphism of A, so a morphism of commutative differential graded algebra from A to A, with a property that on the nth cohomology group, phi induces multiplication by alpha to the n. Then A is formal. So, well, I haven't told you what formality for a CDGA is, but it's really exactly the same definition as formality for a DG operad. I mean that A is connected to its cohomology by a zigzag of quasi-isomorphisms of CDGAs. And exactly as for DG operads, it turns out you only need a length 2 zigzag. So that's a cool theorem. It tells you that, well, if I, by any way I can, if I can produce such an endomorphism of A, I mean, usually it's not obvious how to do that, but if I can, then my algebra is formal. So in some sense, it tells you that in order to prove formality, it's usually useful to have access to many automorphisms of your CDGA. yes, yeah. By endomorphism, I mean a morphism from A to A, a morphism of CDGA from A to A. And here's a sketch of the proof. So, well, the first step is to replace A by what's called a minimal algebra, a minimal model of A. So, well, that's going to be a CDGA, which is this particular form. So it's free. Like if you forget the differential, it's free on a finite tab graded vector space. So a vector space which is finite dimensional in each degree. And then there is a differential with this property. It's called being decomposable. So the differential has to be a derivation with respect to the product. So it's determined by what it does on the geometers, on the elements of V. And being minimal, I mean, it's not all the definition of being minimal, but being minimal implies in particular that it sends V to elements of degree at least, of weight at least 2 in the symmetric algebra. And it's a standard result in rational homotopy theory that you can, for any CDGA that satisfies these conditions, you can find such a minimal algebra and a quasi-isomorphism to A. And then by abstract nonsense, it turns out that you can lift your endomorphism phi to an endomorphism of M, phi tilde, which is going to induce the same map on cohomology. So what this means is, in fact, you can assume that if you want, you can assume that A is minimal. And if you have phi on A, you will have phi on some minimal replacement of A. And then using minimality of M. So if you're not very familiar with minimal models of CDGAs, well, you can just take this for granted. But what you can show using minimality, if in degree n on this minimal model, the only eigenvalues of this lift are going to be of the form alpha to the k, with k greater than or equal to n. So now what I can do is inside m to the k, like inside the degree k elements in M, I consider the subspace the general eigenspaces for the eigenvalues alpha k, with k strictly greater than n. So I told you mk, the eigenvalues we'll have are either from alpha k for k greater than or equal to n. And I consider a subspace of those corresponding to the eigenvalues that are strictly greater than n. And it turns out that this subspace is a DG ideal of M. So if you forget, it's a sub complex, and if I forget the differential, it's an ideal of this commutative algebra. And because of what we know about the cohomology of M, it turns out that this map, the quotient map from M to M mod I, is a quasi-isomorphism. So it's an isomorphism in cohomology. And the reason is somehow in I, we've put all the generalized eigenspaces corresponding to the eigenvalues that do not appear in cohomology. So somehow we've modded out by all the eigenvalues that should not contribute to cohomology. And this quotient is going to have a trivial differential. The reason is the differential has to be compatible. It has to send a generalized eigenspace to a generalized eigenspace for the same eigenvalue, because it commutes with this endomorphism of phi tilde. So in fact, we have produced our zigzag. So we have A, we have this minimal model M, and then we have this quotient map to M mod I, and M mod I has a trivial differential. So it's going to be actually isomorphic to the cohomology of A. So that's a sketch of the proof of this theorem. So if we have such an endomorphism, we can produce a zigzag like this. Okay, and well, this is important because let me remind you a little bit about rational homotopy theory. So we have this definition due to Sullivan that to any space we can assign a CDGA called omega star PL of X, which knows everything about the rational homotopy type of X. And we said that a space is formal if this, sorry, it should be omega star PL of X is formal as a CDGA. And so we can try to use this theorem of Sullivan to prove that some spaces are formal. And I'm going to give you an example which is ridiculously trivial. But I'm going to try to prove it using Sullivan's criterion. So my example is going to be a circle. And so, okay, so let me try to prove that this circle is formal in that sense. So I have this CDGA omega star PL of S1. And I'm going to try to construct interesting automorphisms of the CDGA in order to be able to apply this theorem here. And well, it turns out that, well, we can try to use automorphisms of the space S1 itself. The problem is that the space S1 itself has few automorphisms. So if you try to compute homotopy classes of maps from S1 to S1, well, this is somewhat wrong, sorry. I mean, yeah, if homotopy classes of maps from S1 to S1 is identified with Z via the degree. But if among those maps, if I want to restrict to those that are automorphisms in the homotopy category, I'm just going to have 1 and -1. So I have a group which is isomorphic to Z mod 2. So here I should put a cross or something. So I'm considering the among those among endomorphisms of S1, I'm looking at automorphisms, and I get this group Z mod 2. And the non-trivial element of Z mod 2, it acts by multiplication by -1 on the first cohomology group of S1. So the problem is -1 is not an element of infinite order. So this criterion is not going to be satisfied. So, okay, so that's not so good. Even in this very stupid example, we can't apply this criterion. But in fact, there is a trick that can save the day. It turns out that S1 is what's called the Ellenberg-MacLane space KZ1. So this is the only homotopy type which has pi1 isomorphic to Z and all higher homotopy groups trivial. And it turns out that the map, well, you have a map from KZ1 to KQ1. So KQ1 is defined similarly. It's the only, up to homotopy, it's a unique homotopy type, which is connected and has pi1 isomorphic to Q on all higher homotopy groups trivial. And there is a map from KZ1 to KQ1, which induces an isomorphism in rational cohomology. So instead of using S1, we could use this object. So we can try to prove that this CDGA is formal. And in fact, this is much better because this space KQ1, it has a lot more automorphisms. It's acted on by the group of units of Q. So of course, well, the group of units of Q acts on Q as an abelian group, so it will act on this homotopy type. You can make everything suitably functorial so that this is true. So then I can pick any unit in Q which is not -1 or 1. So any such unit will be of infinite order. And then the action of alpha will induce an action on A, which will satisfy the hypothesis of Sullivan theorem. And that's how you can prove that S1 is formal using the theorem I had here. Okay, so we can try to generalize a little bit this trick of replacing this space by this space. let me tell you a little bit about rational homotopy theory. So yeah, here's the definition. To any simply connected space, there is a unique up to homotopy space that's denoted x lower q with a map from x to x lower q, such that this map induces an isomorphism in rational homology or cohomology. And the homotopy groups of that space, xq, are rational vector spaces. And maybe I should say xq is also simply connected. So at the level of homotopy groups, we're just, well, I mean, this is not part of the definition, but this will be true. This space xq, its homotopy groups will just be the homotopy groups of x tensored with q. This map will be an isomorphism in rational cohomology. So this is a generalization of this trick of going from kz1 to kq1. That's something you can do for any simply connected space. Yeah, maybe you should, if you're listening carefully, you should maybe make a remark. But I've cheated a little bit here because I've stated this theorem of Sullivan for simply connected CDGAs, and I've applied it to a space S1, which is not simply connected. So yeah, let me not worry too much about that. It turns out in that case, Sullivan, like the proof I've given works fine. You can also find a minimal model. But in general, it's usually an issue to find minimal models for non-simply connected space. So yeah, let me avoid this and just move on. So it turns out there is a similar thing you can do for mod P cohomology, but maybe let me skip this at the moment in the interest of time. And let me make a remark. So this theory of turning a homotopy type, so this is what's called usually rationalization of a homotopy type. This extends to non-simply connected spaces, but there are several non-equivalent ways to extend it. And it's a bit more technical, so I'm not going to dive too much into this. But the other remark that we can make is that this rationalized space, xq, typically it will have more automorphisms than x. So we've seen an example here, where this space, its automorphism is just z mod 2. In this space, its automorphism group is q cross. So it's much bigger. Okay. So now let me tell you about operads. It turns out that you can adapt Sullivan theorem that I've stated in the previous slides. You can adapt it to operads. And that's an observation which is due to Dan Pedersen. So if you have a finite type operad, so by this I mean that each space has finite types, so its homology is finite dimensional in each degree. And I assume that in RT1, all I have is the one-dimensional vector space generated by the identity. So P is a finite type DG operad over K. And assume that I have alpha, an element of infinite order in the units of K, and phi, an endomorphism of P, so a map from P to P, a map of DG operads from P to P, which in homological degree n is given by multiplication by alpha to the n. Then P is formed. And the proof, well, the proof is exactly the same proof as Sullivan's. You just have to develop enough of the theory of minimal models for DG operads. It turns out that this condition that in RT1 all you have is the identity. This is what replace the simply connected assumptions that we had in Sullivan theorem. So we had this simply connected assumption here, and in the case of operads, it gets replaced by this condition. Okay, so I'm not going to tell you more about the proof, but if you know about the minimal models for DG operands, you'll be able to adapt the proof in an obvious way. Okay, so now we can try to use this trick to prove formality of the little 2-disk operand in the same way as we've proved formality of the circle. And we sort of run into the same kind of difficulty. So here's a theorem that, well, I think the only available proof in the literature is in a paper of mine, but I think probably was known to people before I wrote it. But the theorem is saying the following. If you try to compute the group of automorphisms as a little 2-disk operand in the homotopy category of operands, what you find is the group Z mod 2. And more precisely, you have an obvious comparison map from the automorphisms of D2 to the automorphisms of the space of array T2, which is a homotopy equivalent to a circle S1. So I told you the space of array T2 elements in the 2-disk operand, I told you it's homotopy equivalent to a space of configurations of 2 points in the plane. And of course, up to homotopy, you can always fix 1 point to be at the origin. So this will be a homotopy equivalent to a space of 1 point in the complement of the origin. And that's homotopy equivalent to S1. So this space this group is Z mod 2. And what I'm saying is that this restriction map is an isomorphism. So you see, we sort of run in the same problem that the 2-disk operand has very few automorphisms. But what's cool is so we can use the same trick to fix this problem. So maybe let me tell you a few words about how we prove this theorem, because that's going to be important in order to prove the generalization, like the rational version later. So yeah, it turns out that these spaces D2n. So I told you they're homotopy equivalent to the spaces of configurations of n points in the plane. And it turns out that this space is also homotopy equivalent to KPN1. So so it's the same notation as before. It's the Ellenberg-MacLane space. The space with only one homotopy group, which is pi1 is isomorphic to Pn. And here Pn is the pure braid group. So these spaces, their higher homotopy groups are 0, and pi1 is the pure braid group. And from this observation, it turns out that we can construct an operand in groupoids. So we can't quite construct an operand in groups, but we can construct an operand in groupoids that's denoted PAB that models those disks operand. And what I mean by model is if I apply the classifying space functor to this operand in groupoids, I find a topological operand which is weakly equivalent to the little disks operand. And then, well, it turns out that this operand is cofibrant and fibrant in a suitable model category for operands in groupoids. So we can compute automorphisms of D2 as automorphisms of this operand PAB. And since this operand PAB will be cofibrant and fibrant, this will actually be automorphisms of PAB modulo homotopy. So that's using the theory of model categories. And then it turns out that PAB has a nice presentation. That's, I mean, this operand PAB was introduced by Drinfeld, and the presentation for this operand was also described by Drinfeld. So we can explicitly compute what this is. Yeah, so let me not tell you exactly what this operand PAB is, but PAB stands for parenthesized braids. So it's sort of built. Its objects are like it's the groupoids that appear. They're homotopy equivalent as groupoids to the pure braid groups, but they have several objects. So there are several object versions of the pure braid group. Okay, and it turns out that exactly the trick we've used to prove that the circle is formal, we can also apply to the little disks operand. So here's a definition. Well, it turns out that there is a group called the Grothendieck-Teichmüller group, which is equipped with a surjective morphism to the groups of units of Q called the cyclotomic character. And here's a theorem, which is due to Drinfeld and Benoit Fraisse. If I compute the group of automorphisms of the operad of little two disks rationalized in the homotopy category of operads, it is isomorphic to the Grothendieck-Teichmüller group. And we have, in fact, a more precise statement. So I have here, if I take automorphisms of this rationalized little two disks operad in the homotopy category of operads, this is isomorphic to this Grothendieck-Teichmüller group. And as before, I can restrict to automorphisms of the space of reality 2, the space of reality 2 operations. So as before, well, this is a rationalization of the circle, which is the space that we've seen before, KQ1. So the automorphism of this is the units of Q. And in fact, this map is the cyclotomic character. In particular, it is surjective. And well, it turns out that this theorem is proved exactly, well, that's not quite how Fraisse proves it, but you can prove it in sort of by mimicking this proof here. So I'm not going to tell you too much about this. But so if what's important is that for any unit of Q, you can lift it to an automorphism of the rationalized little two disks operad. So you see that this group is actually much bigger than Z mod 2 because it surjects to something which is infinite. And in fact, well, this is also much bigger than this because the kernel of this map is actually huge. I'm not going to tell you. It contains something which is isomorphic to a freely algebra and infinitely like a countable family of generators. So this kernel is actually huge. So this group is very big and very complicated. But now, if you believe this, here's the theorem you can prove, and this is a new proof of this theorem that I've stated at the beginning, which is due to Dan Pedersen. So it's quite a recent proof. The operad of chains on D2 is formal. And well, we sort of use the same trick as what we did for the circle. We prove instead that this operad is formal, where PABQ is some model for the rationalized little two disks operad. And this DG operad here is going to have an action of this big group, GTQ. So what we do is we pick an element alpha in the units of Q, which is not 1 or -1, so that it has infinite order. We pick an element of GTQ that lifts alpha, such that when I apply the cyclotomic character, I get alpha. And then, well, this gives me an endomorphism of this operad. And it turns out that in degree I, if I look in arity 2, in degree, sorry, it should be HI of phi applied to this HI of D2 will act by multiplication by alpha to the I. And that's just because of this. So this action is sort of complicated, but if I restrict it to arity 2, it's sort of very easy to understand. So we can understand how phi act on homology in arity 2. But then we can use the observation that I've made at the very beginning. I've told you the homology of the little two disks operad. As an operad, it's generated by arity 2. So in fact, once we know how the Grothendieck-Teichmüller acts on the homology in arity 2, we can extend this to the whole homology operad, to the whole Gersten-Haber operad. And what we deduce is that HI of phi acts by multiplication by alpha to the I on HI of D2n for any I and n. And therefore, we're precisely in the situation where we can apply Petersen criterion for formality. So that's a new proof of this formality result of Kontsevich and Tomrakin. And what you see is modulo this difficult theorem. It's essentially, I mean, it's a very easy proof. And in fact, what you see that you don't even need, I mean, you don't need to know that this is an isomorphism. You just need to know that there is a map like this, which is something easier. So that's something which is already in Greenfeld's paper. And proving an isomorphism here is what Fraisse does. Okay. So maybe I have 5 more minutes. I started a bit late. I mean, so
yeah, you have them.
Okay.
Oh.
So yeah, so far I've told you what other people have done. Maybe let me say a few words about some work of mine and collaborators. So you can try to sort of adapt these ideas in positive characteristic. And here's a somewhat easy proposition. The operad of the two disks with coefficients in a field of positive characteristic is not formal. And the proof is not hard. So in fact, if it were formal, we could just restrict to what happens in RTP. And we would have a quasi-isomorphism between chains on the space of RTP operations and homology of that space, which is equivariant with respect to the symmetry group. So part of the structure of an operad is this equivariance with respect to the symmetry group. So if this operad were formal, we would have such a quasi-isomorphism. But it turns out that yeah, if I take sigma p homotopy orbits on this side, what I will get is something which is finite dimensional, because it turns out that yeah, the singular chain functors it will commute with sigma p homotopy orbits. So I can put the sigma p homotopy orbits inside, and sigma p actually acts freely on this space. So this will be the same as chains over the quotient. And this quotient is homotopical to the space of unordered configurations in the plane. And that's homology. The homology of that, so that space is a manifold, so it will have finite dimensional homology. So this left-hand side has finite dimensional homology. But if you look at this right-hand side, I mean, I'm just looking at homology. So this homology is like a direct sum of each homology group. In particular, H0 is K with a trivial sigma p action. So when I take sigma p homotopy orbits, I have a summand which is going to be the homology of a symmetry group with coefficients in K. And that thing is infinite dimensional. It's sort of a well-known computation. If I take homology of a symmetry group with coefficients in a field of characteristic P, this is infinite dimensional. So this is impossible. And you could think maybe, so what I've explained is, it's telling you that the problem sort of comes from a symmetry group action. But in fact, there is a theorem of Salvatore that tells you that even as a non-symmetric operad, so if I forget the symmetry group actions, chains on D2 with coefficients in a field with 2 elements is not formal. So there is not too much hope to prove that, I mean, yeah. You have to be a lot less optimistic about what you can prove in positive characteristic. But still, here's a theorem that we prove with Johanna Cirisi. Yeah, we prove that the chains on the little 2 disks operad with coefficients in the finite field of P is P minus 2 formal. So what this means is there exists a zigzag of operad morphisms connecting chains over FP and homology of, sorry, here it should be FP. Chains over D2 and homology over D2. And these maps, they're not quite quasi-isomorphisms, but they induce isomorphisms in homology in degree less than or equal to P minus 2. So the usual definition of formality would be infinity formal. And in characteristic 0, the operad of the little 2 disks is infinity formal. In characteristic P, it's P minus 2 formal. And in fact, you can prove that this, like using this observation here, you can prove that this result is sharp in the sense that it's not p-1 formal. So of course, well, if p is 2, this doesn't tell you anything. 0 formal is not saying anything. Yeah, when p gets bigger, this is more and more formal in some sense. And the proof is very similar to what I've just explained. You can replace rationalization of D2 by something called P completion of D2. It's sort of an analog of the rationalization that I've explained at the beginning. It's something you can replace Q by FP and get something called P completion. And when I P complete this the little two-disk operator, I have a group that acts, which is called the profinite Grothendieck-Teichmüller group. So it's a variant of the Grothendieck-Teichmüller group I've introduced before. And this profinite Grothendieck-Teichmüller group has an action. I mean, it maps surjectively to this group of units of FP cross. And in fact, the problem now is contrary to Q cross, which had elements of infinite order. Any element in FP cross has finite order. But what we can do is pick an element of maximal order, lift it to GT hat, and this will give us an automorphism of this object, and therefore an automorphism of this object. And then we can adapt Peterson's argument. So Peterson's argument, it tells us that when we have an alpha that has infinite order, we get from full formality. And what we prove with Johanna is if we only have an element of finite order, we'll get a partial formality result of this form. So this is sort of how things work in that case. So we get a formality result in positive characteristic. Maybe let me just state without saying more, but it turns out we can also generalize this to higher dimension little disks of Rad. So that's joint work with Pedro Boavida de Brito. Yeah, what we show is if we replace the little 2 disks of Rad by the little n disks of Rad, using the same kind of ideas, we can prove that chains on that thing is formal as a DG opera. So that was a theorem that was due to Kontsevich. I mean, as usual, it was like a sketch of proof by Kontsevich and a formal proof by Pascal Lambrechts and Ismar Volic. And what we can do is, well, we recover, like we give a new proof of this, and also in positive characteristic, we show that these operas are n-1 times p-2 formal. And the proof is completely similar. We produce action of these Grothendieck-Teichmüller groups that behave in a way that let us apply a Peterson criterion or the version that we proved with Johanna. All right, I think I'll stop here. Thank you very much for your attention.
Okay, thank you, Geoffroy.